Changes occurred in the National Electrical Code, specifically between the 1999 and 2005 editions, concerning calculation methodologies within Section 220. The primary revisions involve updates to tables and sections that influence how electrical loads and conductor ampacities are determined. Firstly, Table 220.12 underwent revisions to incorporate new ampacities for conductors installed in cable trays and raceways. This update means that the allowable current carrying capacity for conductors in these types of installations may differ between the 1999 and 2005 editions of the code. Therefore, it is crucial to consult the 2005 NEC to ensure compliance with the updated ampacity ratings when designing or evaluating electrical systems involving cable trays and raceways. Secondly, Table 220.19 was revised to include new ampacities for conductors used in underground ducts. Similar to the changes in Table 220.12, this revision affects the allowable current carrying capacity of conductors specifically installed in underground duct systems. Electrical professionals should refer to the 2005 NEC to ascertain the correct ampacity values for conductors in these underground installations, as the values provided in the 1999 NEC may no longer be accurate. Thirdly, Section 220.61 experienced revisions aimed at clarifying the requirements for calculating the ampacity of conductors used in paralleled sets. Paralleling conductors is a technique employed to increase the overall ampacity of a circuit. The updated Section 220.61 in the 2005 NEC provides more explicit guidelines on how to properly calculate the ampacity of these paralleled conductor configurations, ensuring that the installation meets safety standards and can handle the intended load. Fourthly, Section 220.82 was revised to include new requirements for calculating the ampacity of conductors used in flexible cords and cables. Flexible cords and cables are commonly used for connecting appliances, portable equipment, and other devices. The 2005 NEC introduced revised requirements for calculating the ampacity of these flexible wiring methods, potentially impacting the selection and application of flexible cords and cables in various electrical systems. In addition to these specific table and section revisions, general changes were implemented in the 2005 NEC that affect how calculations are performed. One notable change is the mandate for utilizing the metric system in all calculations. This means that electrical professionals are expected to perform calculations using metric units such as meters, kilograms, and amperes, rather than customary units like feet, pounds, and amps. The transition to the metric system aims to promote consistency and standardization in electrical calculations, aligning with international practices. It is essential to recognize that the aforementioned changes represent only a portion of the modifications made to Section 220 of the NEC between 1999 and 2005. The NEC undergoes regular updates to reflect advancements in technology, address safety concerns, and improve clarity. To ensure compliance with the latest requirements and best practices, it is always advisable to consult the most recent edition of the NEC. Using an outdated version of the code, such as the 1999 NEC, may result in installations that do not meet current safety standards or violate applicable regulations. The specific changes outlined in the previous points involve Table 220.12, Table 220.19, Section 220.61, and Section 220.82. For Table 220.12, the revisions pertain to conductor ampacities within cable trays and raceways. Cable trays and raceways are support systems used to route and manage electrical cables and conductors. The ampacity of conductors in these systems depends on factors such as conductor size, insulation type, ambient temperature, and the number of conductors bundled together. The updated ampacity values in the 2005 NEC may differ from those in the 1999 NEC due to changes in these influencing factors or refinements in the calculation methods. For Table 220.19, the revisions focus on conductor ampacities within underground ducts. Underground ducts are conduits or channels used to encase and protect electrical conductors buried beneath the ground. The ampacity of conductors in underground ducts is affected by factors such as soil thermoresistivity, burial depth, and ambient earth temperature. The updated ampacity values in the 2005 NEC may reflect changes in these factors or improvements in the modeling of heat dissipation in underground installations. For Section 220.61, the revisions clarify the calculation of ampacity for parallel conductors. Paralleling conductors involves connecting two or more conductors in parallel to increase the overall current carrying capacity of a circuit. When paralleling conductors, it is essential to ensure that the conductors are of the same material, size, and insulation type, and that they are properly terminated to ensure equal current sharing. The revisions in Section 220.61 provide more specific guidance on how to calculate the ampacity of parallel conductors while accounting for factors such as conductor spacing, termination methods, and directing adjustments. For Section 220.82, the revisions address the calculation of ampacity for conductors in flexible cords and cables. Flexible cords and cables are used to connect portable appliances, equipment, and devices to a power source. The ampacity of conductors in flexible cords and cables is influenced by factors such as conductor size, insulation type, ambient temperature, and the presence of other heat-generating components. The revisions in Section 220.82 may include updated ampacity tables or adjustments to directing factors to ensure that flexible cords and cables are appropriately sized for their intended applications. Beyond the specific changes to tables and sections, the 2005 NEC also introduced a general requirement for using the metric system in all calculations. This change aligns the NEC with international standards and promotes consistency in electrical engineering practices. The metric system, also known as the International System of Units or C, is a decimal-based system of measurement that uses units such as meters for length, kilograms for mass, seconds for time, amperes for electric current, and kelvins for temperature. The use of the metric system simplifies calculations and reduces the potential for errors that can arise when converting between different units of measurement. In summary, the changes from the 1999 NEC to the 2005 NEC in Section 220 involved revisions to tables and sections related to conductor ampacity calculations, as well as the introduction of a general requirement for using the metric system. These changes were intended to enhance the safety, accuracy, and consistency of electrical installations. Consulting the latest edition of the NEC is crucial for ensuring compliance with current standards and best practices. When performing electrical calculations, always refer to the appropriate tables and sections in the NEC and adhere to the specified requirements and guidelines. Remember that electrical codes and standards are subject to change, and it is the responsibility of electrical professionals to stay informed about the latest updates and revisions. Engaging in continuing education, attending industry training sessions, and participating in professional organizations can help electrical professionals maintain their knowledge and skills and ensure that they are providing safer and compliant electrical services. Additionally, it is important to consult with qualified electrical inspectors and engineers to obtain guidance and clarification on specific code requirements and installation practices. Working collaboratively with these experts can help ensure that electrical projects are designed, installed, and maintained in accordance with all applicable codes and standards. The aforementioned revisions to tables and sections underscore the importance of understanding the factors that influence conductor ampacity. Conductor ampacity is the maximum amount of current that a conductor can carry continuously without exceeding its temperature rating. The temperature rating of a conductor is the maximum temperature that the conductor's insulation can withstand without degrading or failing. Exceeding the temperature rating of a conductor can lead to insulation damage, conductor melting, and potentially fire hazards. Several factors affect conductor ampacity, including conductor size, insulation type, ambient temperature, the number of conductors bundled together, and the presence of other heat-generating components. Conductor size is a primary determinant of ampacity, with larger conductors generally having higher ampacity ratings. Insulation type also plays a significant role, as different insulation materials have different temperature ratings. Conductors with higher temperature ratings can carry more current than conductors with lower temperature ratings. Ambient temperature affects conductor ampacity because higher ambient temperatures reduce the conductor's ability to dissipate heat. The NEC provides ampacity correction factors that must be applied when conductors are installed in environments with ambient temperatures above 30 degrees Celsius or 86 degrees Fahrenheit. The number of conductors bundled together also affects ampacity because bundled conductors generate more heat than isolated conductors. The NEC provides ampacity dilating factors that must be applied when multiple conductors are installed in close proximity to each other. The presence of other heat-generating components such as lighting fixtures, transformers, and motors can also affect conductor ampacity. These components can raise the ambient temperature in the vicinity of the conductors, requiring additional ampacity dilating. In addition to understanding the factors that influence conductor ampacity, it is also important to be familiar with the different types of conductors and their applications. Conductors are classified according to their material, insulation type, and stranding. The most common conductor material is copper, which offers excellent conductivity and corrosion resistance. Aluminum conductors are also used in some applications, particularly for larger sizes where weight is a concern. Insulation types include thermoplastic, thermoset, and rubber. Thermoplastic insulation is commonly used for general-purpose wiring, while thermoset insulation is used for high-temperature applications. Rubber insulation is used for flexible cords and cables. Conductor stranding refers to the number of individual strands that make up the conductor. Stranded conductors are more flexible than solid conductors and are less likely to break when bent or twisted. The NEC provides detailed requirements for conductor selection, installation, and termination. These requirements are intended to ensure that conductors are properly sized and protected to prevent overheating, electrical faults, and fire hazards. When selecting conductors, it is important to consider the specific application, the operating conditions, and the applicable code requirements. Always consult the NEC and other relevant standards to ensure that conductors are installed safely and in compliance with all applicable regulations. Furthermore, it is essential to understand the principles of electrical calculations and load management. Electrical calculations are used to determine the size of conductors, overcurrent protection devices, and other electrical components. Load management involves balancing the electrical load on a circuit to prevent overloading and voltage drops. The NEC provides guidelines for performing electrical calculations and managing electrical loads. These guidelines are based on established engineering principles and are intended to ensure that electrical systems are safe, reliable, and efficient. When performing electrical calculations, it is important to use accurate data and to follow the prescribed procedures. Always double-check your calculations and consult with a qualified electrical engineer if you have any questions or concerns. Load management is particularly important in large electrical systems such as those found in commercial and industrial buildings. By carefully managing the electrical load, it is possible to reduce energy consumption, improve power quality, and extend the life of electrical equipment. Load management techniques include load shedding, load shifting, and peak shaving. Load shedding involves disconnecting non-essential loads during periods of high demand. Load shifting involves moving loads from peak periods to off-peak periods. Peak shaving involves using on-site generation or energy storage to reduce the peak demand on the utility grid. In conclusion, the changes from the 1999 NEC to the 2005 NEC in Section 220 highlighted the importance of staying up to date with the latest electrical codes and standards. These changes involved revisions to tables and sections related to conductor ampacity calculations, as well as the introduction of a general requirement for using the metric system. By understanding the factors that influence conductor ampacity, selecting appropriate conductors, and performing accurate electrical calculations, electrical professionals can ensure that electrical systems are safe, reliable, and efficient. Remember to consult the NEC and other relevant standards, and to work collaboratively with qualified electrical inspectors and engineers. Staying informed and maintaining a commitment to safety and excellence are essential for success in the electrical industry. The transition to the metric system in the 2005 NEC represents a significant step towards standardization and international harmonization. The metric system is the dominant system of measurement used throughout the world, and its adoption in the NEC aligns the code with global practices. The metric system offers several advantages over customary units, including simplicity, consistency, and ease of conversion. The metric system is based on a decimal system, which means that units are related to each other by powers of 10. This makes it easy to convert between different units, such as millimeters, centimeters, meters, and kilometers. In contrast, customary units are based on a variety of different systems, which can make conversions more complex and prone to errors. The NEC provides conversion factors for converting between customary units and metric units. These conversion factors can be found in the NEC Annex. When performing electrical calculations, it is important to use the correct units and to ensure that all units are consistent. Mixing customary units and metric units in a calculation can lead to errors and potentially unsafe results. In addition to using the metric system, the 2005 NEC also introduced other changes aimed at improving the clarity and consistency of the code. These changes included revisions to definitions, terminology, and formatting. The goal of these changes was to make the NEC easier to understand and to reduce the potential for misinterpretations. The NEC is a complex and comprehensive document, and it is essential to have a thorough understanding of its provisions. Electrical professionals should invest the time and effort necessary to become familiar with the NEC and to stay up to date with the latest changes. The NEC is updated every 3 years, and each new edition incorporates revisions and additions that reflect advancements in technology, address safety concerns, and improve clarity. Staying current with the NEC is essential for ensuring that electrical installations are safe, compliant, and efficient. In addition to reading the NEC, electrical professionals should also participate in continuing education courses and attend industry training sessions. These activities can help to reinforce their knowledge and skills and to keep them informed about the latest developments in the electrical industry. Electrical codes and standards are constantly evolving, and it is important to be a lifelong learner in order to maintain professional competence. The electrical industry is also undergoing significant changes due to the increasing adoption of new technologies such as renewable energy, energy storage, and smart grids. These technologies are transforming the way that electricity is generated, distributed, and consumed. Electrical professionals need to be prepared to work with these new technologies and to adapt their skills and knowledge accordingly. The NEC is also evolving to address the challenges and opportunities presented by these new technologies. The NEC includes provisions for the installation and operation of renewable energy systems, energy storage systems, and smart grid technologies. Electrical professionals need to be familiar with these provisions in order to ensure that these systems are installed safely and in compliance with all applicable codes and standards. The electrical industry is a vital part of the economy, and electrical professionals play a critical role in ensuring the safety and reliability of the electrical infrastructure. By staying informed, maintaining their skills, and adapting to new technologies, electrical professionals can continue to contribute to the success of the industry and to the well-being of society.